Section 12.1, the vector valued function. Okay, so to get us started here, let's consider a line in R3 in parametric form. Okay, so for example, x is equal to -1 plus t, y is equal to 3t, and z is equal to 2 minus 4t. Okay, we know this is a line because each of these variables, x, y, and z, is defined as a linear function of t. So x, y, z are each a linear function of t, right? Okay, so let's change it up a little bit. What if I gave you this? What if I said x is equal to -1 plus t squared, y equal to 3t, and z equal to 1 over t. Now what? Well, clearly this is not a linear function. It's not a line. So it's not a line. But it does represent a curve. But does represent a curve. Now, it's not a surface, you know, we have full-on equations for those. This is not a surface, this is just a curve. It's just not a straight line. So, not a surface. All right, so we have this curve in space, and each of these is represented as functions of t, okay? So any curve in space can be represented this way. Can be represented, there we go, represented parametrically as x equal to some function of t, we'll call it f of t, y equal to another function of t, g of t, and z equal to another function of t, we'll call it h of t. Okay? And these are going to be the components of a vector valued function. So we're going to represent these curves using vectors. And that's going to allow us to kind of see the motion along a curve. All right, so I'll explain in just a moment. Let's go ahead and write this down. Our vector valued function, which we are going to represent with r of t, is equal to f of t in the I direction, so that's our x component, plus g of t in the j direction, that's our y component, plus h of t in the k direction, that's our z component, okay? All right, so if you drop one of these off, this is R3. If you were to drop off the k component, we would just be working in the plane. So we can represent planar curves this way as well. Now, these functions f, g, and h, as I said, are called component functions. Okay? So these are kind of corresponding to our real numbers, our components that we had. These themselves are not vectors. F, G, and H are not vectors. They are just components. Okay? And we can write R of t in component form as f of t, g of t, h of t. Okay, so we can represent it in component form just like this. Now, because the curves are parameterized, they have an orientation. So because the curves are parameterized, they have an orientation. Okay, they have a direction. And you might even think of it as having speed, because different curves can move around at different speeds. That was weird. Okay. They have direction and speed, if you will. So we can use this to describe motion along a curve. So we can tell how quickly the path is taken and where that path starts, where that path ends, and how quickly, you know, the particle or whatever it is that's moving along this path moves through this. Okay. All right, so just because two vector valued functions represent the same curve does not mean they are equivalent functions. So let me give you an example of that. So I'm going to give you two vector valued functions that represent the unit circle. Okay, so here we go. We have r of t. Let's call this r1 since I'm doing two of them. r1 of t equal to sine of t in the I direction plus cosine of t in the j direction. And r2 of t will be equal to cosine of t in the x direction minus sine of t in the y direction. That's why I should say in the j. There we go, in the j direction. All right, so we're going to see that both of these represent the unit circle, but they represent different ways of forming the unit circle. So these are technically different functions, even though they represent the same curve. So let's take a look here. All right, we're going to limit ourselves to t between 0 and 2 pi. Okay. And I'm going to go ahead and set these up. So t, x, y. All right, so let's begin at 0, and we'll just go in pi over 4 increments. So pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, and 2 pi. Okay, so I'll go ahead and put these in. This is for R1. So the x component is sine of t. So sine of 0 is 0. Sine of pi over 4 is root 2 over 2. Sine of pi over 2 is 1. Sine of 3 pi over 4 is root 2 over 2. Sine of pi is 0. Sine of 5 pi over 4 is negative root 2 over 2. Sine of 3 pi over 2 is negative 1. Sine of 7 pi over 4 is negative root 2 over 2. And sine of 2 pi is back to 0. Cosine will follow its pattern. So cosine of 0 is 1. Then root 2 over 2, 0, negative root 2 over 2, negative 1, negative root 2 over 2. There we go. Try to fix it. Negative root 2 over 2. There we go. Back to 0, positive root 2 over 2, and then back to 1. So if we were to sketch this curve, and this is a planar curve because I do not have an x component. So if we were to sketch this curve, say this is 1 and 1, we begin at the point 0, 1. So that's our starting point. So we want to make that nice and big so we know that's our starting point, 0, 1. The next point is root 2 over 2, root 2 over 2. So that means we're traversing this curve in a clockwise direction. Okay, next point is 1, 0, moving right along. All right, so you can see that we are forming this with direction. So we're going to go ahead and sketch in our curve. And we went around one time, so we'll just put a single arrow occasionally showing that we went around the curve. Okay, so now let's take a look at R2. So we have our t, our x, and our y. For simplicity, I'll do the exact same values. 0, pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, and 2 pi. Okay, so now the x component is given by cosine of t. So cosine of 0 is 1, and then it'll follow its pattern through, same as before. Okay, and then now we have y component is given by negative sine of t. So negative sine of t. Sine of 0 is 0, so that's 0. Sine of pi over 4 is root 2 over 2, so this will be negative root 2 over 2. Then we have sine of pi over 2, which would be 1, so this will be negative 1, and it's going to continue in this way. There we go. Okay, so now we can sketch this curve. So this curve begins at, I'm going to draw it over here in the middle so we can compare. So this one was R1 of t. So now we're going to sketch R2 of t. So this one begins at 1, 0. So make a nice big dot there. And then it moves to root 2 over 2, negative root 2 over 2. 0, negative 1. Negative root 2 over 2, negative root 2 over 2, and it's going to continue around the curve just like this. Okay. So this curve is also going to travel in a clockwise direction. And in here. Okay, so as you can see, these are extremely similar curves. They both represent the unit circle. They're both traveling clockwise around the curve. The difference is, though, that one begins at the top at the point 0, 1, and one begins at the point 1, 0. So these are different curves. Now, I could give you another one that would travel around faster. So for example, let's do another curve. How about R3 of t equal to sine of t in the I direction? Let's make that 2t. I want it to go faster. 2t in the I direction plus cosine of 2t in the j direction. Now, we can do another table. This one's going to come out exactly as R1 did. The only difference is from 0 to 2 pi, we are going to travel the entire thing twice. So we will come all the way around our circle once, but then we would go around it again. So to represent that, we're going to do a double arrow. Just a double arrow periodically to let people know that that's what we've got going on. Okay, so now let's talk about the domain of the vector valued function. This is just going to be the intersection of the domains of the component functions. So let's write that down. Intersection of the domains of the component functions. Okay, so let me give you an example. Suppose I have r of t. Oh, and r is a vector valued function. It is a vector. So we should be writing that with a little arrow up above the r. I'll add a note to the description for this video so that you guys are aware of that ahead of time. But just to be aware, it is a vector. R of t is a vector. Okay, so r of t is equal to ln of t in the I direction plus square root of 4 minus t in the j direction minus 1 over t minus 1 in the k direction. Okay, so each of these has restrictions on its domain, so each component function does. So ln of t, we have to have t greater than 0. It must be something positive. All right, for the square root of 4 minus t, we know that 4 minus t must be greater than or equal to 0, meaning t must be less than or equal to 4. And then finally, for 1 over t minus 1, we know t cannot be equal to 1 because that would cause us to divide by 0. Big time no-no, right? Okay, so we can't do that. Okay, so let's put all this together. I'm going to do it the old-fashioned way on a number line. You do not have to do this. I'm just doing it as a visualization in case anyone needs a refresher. So we've got t greater than 0, so that's going to be all the numbers greater than 0. T less than or equal to 4, so I come here to 4. This is 0, this is 4, and it's going to be everything in here. And then we have to exclude the 1. So our domain for r of t is going to be given by 0 to 1, exclude the 1, union, 1 to 4, include the 4. And so there's our domain and interval notation. Okay, so let's go ahead and sketch a vector valued function in R3. So let's go ahead and do that. So let's sketch, okay, we have r of t equal to 4 cosine of t in the I direction plus 4 sine t in the j direction plus t in the k direction. Okay, and we're going to do this for t between 0 and 4 pi. All right, so we're going to set it up just as we had done before. So we have our table of values. We've got t, x, and y. And we're going to be doing this from 0 to 4 pi. So I'm going to skip around a little bit, maybe make this a little more intermittent. There it is. Okay, so let's do 0 let's do pi over 2. Let's do pi. 3 pi over 2, 2 pi, 5 pi over 2, 3 pi, 7 pi over 2, 4 pi. Okay, that should give us enough to get a good picture of what's going on here. So for the x components, we have cosine of t times 4. So 4 times cosine of t. Cosine of 0 is 1 times 4 is 4. Cosine of pi over 2 is 0. Cosine of pi is negative 1, so that's negative 4. Cosine of 3 pi over 2 is 0. Cosine of 2 pi takes us back to positive. Okay, so hopefully you can see what's happening here. We are traversing the unit circle. Beginning at the unit circle. No, we are traversing the circle of radius 4 centered at the origin. Okay, and we can do the same thing for y here. So this is sine of t times 4. So we begin with 0, 4, 0, negative 4, 0, 4, 0, negative 4, 0. And we now have a z component, so we need to include that. So this is just t, right? So whatever t is. So 0, pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2, 3 pi, 7 pi over 2, and 4 pi. Okay, there, good. All right, so now if we're going to sketch this graph, we're going to need to do it in 3 dimensions. So let's give it a shot here. Let's see. Just for the sake of being able to look at this better, I am going to draw the z-axis straight up as per usual, but I'm going to draw the x and y axes at slight angles. So I'm going to do y at a bit of an angle, and I'm going to do x at an angle. Okay, so now we can see. So here's our origin right here. So the first point is 4, 0, 0. So I'm going to make one mark out at 4. Probably need to make this one a little bit further out. There we go. Okay, so first point is 4, 0, 0. So x is 4, z and y are both 0. So this is our starting point right here. Then, whenever z is pi over 2, y is going to be 4, x is going to be 0. So I'm going to go ahead and mark off z at pi over 2 increments. So we have 0, pi over 2, pi, 3 pi over 2, pi, 5 pi over 2, 2 pi, 5 pi over 2, 3 pi, 7 pi over 2, 4 pi. Okay. So we've got the first point down. Next point, we're going to come out here to 4, 0, and we're going to go up pi over 2. Okay, so this is the point 0, 4 pi over 2. Then we come out to negative 4, 0 and go up to pi. Okay, so what I'm trying to do, I know it's difficult to see this, but what I'm trying to do is maintain parallel, kind of a parallel line running through z equal to pi so that I can get the exact point that I need in space with this particular perspective. I did the same thing here with my y equal to 4 and z equal to pi over 2. Just trying to keep those running there. Okay, so then we come around a little further, and now we are at 3 pi over 2, so we have negative 0, negative 4, 3 pi over 2. So we're going to come up the equivalent of 3 pi over 2, which should be right about here, I think. Trying to keep it parallel. Right about there. Okay. So what we've done is we are traversing this curve and climbing up as we go. Oh, that was terrible. Try that again. So we're kind of climbing up as we go. So hopefully you can kind of see that happening. Let's continue. So now I've got the point 4, 0, 2 pi. So 4, 0, 2 pi. So this is 2 pi. Bring it down. So we're going to be about here. So the curve will continue and come through about here. There are no sharp curves here. It should be very smooth. It's just my poor drawing skills. 0, 4 pi over 2. So that's going to put us back here. So here's pi over 2. We want to run down parallel. So we're hitting about here-ish. So now my curve comes about here. And then we have negative 4, 0, 3 pi. So 3 pi is approximately here. So I come out to 4 and I go up to meet this line. Okay, so the curve continues here. And then we keep going. We have 0, negative 4, 7 pi over 2. So that'll be approximately here, I think. 7 pi over 2. Oh, no, not high enough. Need to be here. Okay. And then our last point is at 4, 0, 4 pi. So now we're all the way at the top. And we come straight up from 4 here to intersect that. And there's our last point. So now I can close the curve. Okay, so once again, it is very difficult to do this in 2 dimensions, but hopefully you can kind of see what was happening as we were spiraling up and creating a bit of a helix here. So let me go ahead and put in our direction lines. We began at this point at the bottom and worked our way up, and we traversed this entire curve in one pass from 0 to 4 pi. Okay, so now we're going to talk about some of the properties of the vector valued functions, the VVFs, and we're going to talk about the limits and the continuity of those functions. Okay, so properties here. Go back to white. There we go. Okay, so first of all, it follows basic operations. If we have R1 of t equal to F1 of t I plus G1 of t j, right, plus H1 of t k, and R2 of t equal to F2 of t in the I direction plus F2 of t in the j direction plus H2 of t in the k direction, and that's supposed to be a 2. I know it doesn't look anything like it. There we go. Wait a minute, that's supposed to be a G. Let's fix that, shall we? That should be a G. There we go, that's better. Okay, so here are our functions. We have our x components, y components, g and z components. Then, if I were to add those together, r1 of t plus r2 of t, it's just like any other vector. Again, these are all vectors. It's just like any other vector. We just add the corresponding components. So this is going to be f1 of t plus f2 of t, that's my I component vector, or component function, plus g1 of t plus g2 of t, that's the j component, plus h1 of t plus h2 of t in the k direction. Okay, and the same thing would work for negatives. So we could even just make this a plus minus. So it's plus minus, plus minus, plus minus. If you're subtracting, you just subtract the corresponding components. All right, and scalar multiplication works exactly the same way. If we have a real number c, and we have c times r of t, then, let's do r1. Then I have c times f1 of t in the I direction, plus c times g1 of t in the j direction, plus c times h1 of t in the k direction. All right, so all of the standard vector operations hold with the vector valued functions. Nothing changes there. Okay, so now let's talk about limits of the vector valued function. Okay, suppose I have r of t equal to f of t I plus g of t a in the j direction plus h of t in the k direction. Okay, then the limit as t approaches a of r of t is equal to the limit as t approaches a of f of t in the I direction plus the limit as t approaches a of g of t in the j direction plus, see where this is going, the limit as t approaches a of h of t in the k direction. Okay, so it's just the limit of each of the component functions at that value, provided this limit exists. So that's important. If the limit does not exist, then it doesn't exist. Provided the limit exists for all component functions at t equal to a. All right, so analytically, let's write that out. That, you can't read that. I can't read that. No, you can't read it. Let's try again. Analytically, there we go. Analytically, that is, if the limit as t approaches a of r of t is equal to L, capital L, then the magnitude of r of t minus L, and L is a vector because that limit is a vector, then the magnitude approaches 0, the magnitude of r of t minus L approaches 0 as t approaches a. So there's the analytical version. Okay, I think I forgot to hit record there. So let me just jump back just really quickly to make sure I didn't miss this. So we were talking about continuity of a vector valued function. A vector valued function is continuous at a point t equal to a if the limit of that vector valued function as t approaches a exists, and that limit is r of a. So standard continuity at a point. A vector valued function is continuous on an interval if it is continuous at every point on that interval. Okay, so let's do a couple of examples so you can see that in action. Let's consider r of t equal to t in the I direction plus a in the j direction plus a squared minus t squared in the k direction. Is this continuous at 0? All right, so is it continuous at t equals 0? Well, we just take that limit. So we're going to have the limit as t approaches 0 of r of t. So that's just going to be the limit of each component. The limit as t approaches 0 of t in the I direction plus the limit as t approaches 0 of a in the j direction plus the limit as t approaches 0 of a squared minus t squared in the k direction. Okay. So that is going to be 0i plus aj plus a squared k. All right, excellent. So I'll go ahead and write that in component form just for the ease of looking at it. Okay, so that's the limit. Now we have to see, is that limit equal to r of a? So r of, I'm sorry, not r of a, r of 0. We're taking the limit as we go to 0. So r of 0. Okay, well that's going to be 0 in the I direction plus a in the j direction plus a squared minus 0 squared in the k direction, which is equal to 0a squared. So yes, it is continuous at 0. Instead of writing that out, let me just write t equal to 0. There we go. Okay, so another example. Identify the intervals where r of t equal to t in the I direction plus the square root of t plus 1 in the j direction plus t squared plus 1 in the k direction is continuous. The intervals where this function is continuous. Okay, I keep forgetting to put the arrow above r, but r of t is a vector valued function. Okay, so where is this thing continuous? Well, good news is that the x component and the y and the z component are continuous functions. There's no discontinuity there. The square root of t plus 1, that has a domain restriction. So let's take a look there. We've got to have t plus 1 greater than or equal to 0, which means t is greater than or equal to -1. Try that again. There we go. So t has to be greater than or equal to -1. All three components are continuous for all of those intervals, so we are continuous on -1 to infinity. All right, so that'll wrap up this section. If you do have questions, as always, please let me know.